I will turn it over to George Lesniak. Thank you for doing part 4 of our ADAS training series. Take it away, George.
Thank you, Maddie. And good evening, everyone. Thanks for joining us tonight. And thank you for joining us on this continued discussion of ADAS technology and ADAS calibrations. As Maddie pointed out, we are currently on part 4, Introduction to ADAS Calibrations. And this marks the halfway point in our 7-part series. So with that, let's take it away. So we're going to continue this discussion with how do we identify an ADAS vehicle? So the point here is you have a vehicle coming into your shop for a standard repair or service that may impact one or more ADAS systems. So of course, if you're going to give an estimate for the repair or service you're going to perform, it is a very good idea to understand whether or not one or more ADAS calibrations would be required on top of that to not only protect your customers and keep them safe on the road, but to protect your shop from liability. The reason I even built this section of the class is when I first started with Autel a little over 2 years ago now, I did a quick tour of the Raleigh area, stopped at some collision centers, stopped at some new car dealerships, and asked about, what are you guys doing? What is your shop doing for ADAS calibrations? And for the most part, I got a kind of a funny deer in the headlights look. And one collision center, a large national chain, told me, well, we don't see many vehicles with those new systems. And just standing in the shop, I was able to just take a quick scan around and see that more than half the vehicles that they were repairing were in fact equipped with ADAS. So as you get a vehicle in and you're walking out to the parking lot to either start your visual inspection or perform an estimate or pull the vehicle in for repairs, we can start with a visual inspection. And here we're looking for certain items that will stick out to indicate this vehicle is in fact ADAS equipped. Number one is take a peek at the windshield. If you're looking at the frit area, the black band around the windshield, especially where the rearview mirror is mounted, look for those cutouts in the frit that are generally like a cutoff triangle in shape. This particular one you see here has a forward-facing camera, a dual laser, a thermal imager, and a range sensor. So this is a well-equipped vehicle, but there's a tip-off that we're ADAS equipped. Some vehicles might have a radar sensor poking out in the grille. Jeeps, many Nissans, Hondas have a cutout in the grille with a radar sensor behind it, and they're easy to spot. But a lot of other vehicles, Mercedes, BMW, Toyotas, Hyundai, Kias, the radar sensor is behind the grille or behind the bumper and not easily visible without taking something apart. Other vehicles might have either around view monitoring or like the Honda shown here, has a camera in the passenger side view mirror to act as a form of blind spot detection. Honda calls this particular system lane watch. But keep in mind that not all vehicles with around view monitoring have the cameras so easily visible. If you take a look at, for instance, like a Ford F-150, the cameras are on the bottom of the mirror, so you'd have to be down looking up to actually spot that camera. But this is your first method of identifying an ADAS-equipped vehicle. And next, as we get into the car, we would take a look at things like the cruise control stalk. Does it have a button or a knob that might indicate that this cruise control system also has an adjustment for following distance, which would indicate adaptive cruise control? Does the vehicle have ADAS buttons either on the lower dash, the overhead console, or the center console with indicators for things like lane centering or lane departure warning, blind spot detection, things of that nature? Once we power up the vehicle, turn on the ignition, we'll be looking at the malfunction indicator lamps. Now, here it can get a little bit more tricky as pretty much every OE develops their own icon for their malfunction indicator lamps. However, the icons for lane departure warning are either going to look like the yellow and black image on the right or the center button on the lower left image. So those should be fairly easy to pick out. Well, once we get the vehicle in the shop, a great way to identify ADAS systems on the particular vehicle you're working on is to perform a pre-scan or an all-module scan. Some scan tools might call it a DTC scan. Here, using the Autel tool, we can generate a pre-scan report that will identify each of the ADAS systems with the blue ADAS logo and even indicate to us ADAS systems that require recalibration because of current fault codes being present in that module. So this is an excellent way of identifying ADAS systems. But what if the vehicle isn't in your shop yet? What if you're talking to the customer on the phone and you need to generate an estimate? Well, there are some services and apps that you can subscribe to help you identify ADAS equipped vehicles without actually having the vehicle present. But there's some free services as well. The one I want to share with you here is the NHTSA, National Highway Traffic Safety Administration, VIN Decoder. Now, here's the URL, but instead of trying to copy this down, what you would want to do is Google NHTSA VIN Decoder, and it'll be the first item on your Google search. So once we click that link, it'll take us directly to the VIN Decoder where we could enter the VIN from the vehicle we're working on. Now, it will accept a partial VIN. However, a full VIN will give more detailed information. A partial VIN will only provide, at best, the ADAS systems that may be present on the vehicle. If we supply a full VIN, most vehicle manufacturers provide as-built data to NHTSA, and this website will connect to the OE as-built data site and provide exact equipment that's on the vehicle that you are working on, the exact vehicle, not just that particular make and model. So once we enter the complete VIN, we'd hit that blue button that says Decode VIN, and that will give us a basic vehicle overview. This particular overview is basically going to tell us your make and model, the type of vehicle, it's a passenger car, some general information about the chassis, the gross vehicle weight rating, if it's listed, engine, transmission, number of airbags and where they're located. But if we hit the button the blue button again that says show all vehicle details, this will give us an exact breakdown for this vehicle as to which active safety systems are included. So here we would see exactly what systems are on this vehicle, and maybe using our shop information system, we can start looking at calibration procedures to determine if the service we're going to perform is going to affect any of the ADAS systems. You could also look at the service procedures for whether it's a wheel alignment or changing a radiator or an AC condenser, that will also indicate which ADAS calibrations may need to be performed. So once the vehicle is identified, well, we need to talk about the actual ADAS calibration. Now, we're not going to get into the actual calibrations today. That's going to be more like 2 sessions from now. But what is an ADAS calibration and why are we doing what we're doing? Fine, the OE says if we perform a wheel alignment, it needs to be calibrated. But I can tell you that there's a very, very high percentage of shops that completely disregard the OE recommendations, and their rationale is we never had a problem before. A very high percentage of shops are unaware that the basic services that they're performing will require one or more ADAS calibrations. So let's take a look at just one simple system, and I'll try to give you an idea of why these systems need to be calibrated after a simple service like a 4-wheel alignment. So we're going to start by taking a view through the forward-facing camera mounted on the windshield. Now, every camera, whether it's an ADAS camera on a vehicle, the camera on your smartphone, a DSLR, doesn't matter. Every camera has a field of view, the number of degrees of angle that the lens can see horizontally and vertically. Now, when it comes to ADAS forward-facing cameras, most cameras are going to fall in the range of 22-degree angle of view to maybe a 44 or 45-degree angle of view. Few rare exceptions may go to 160 or 170 degrees, so just a wider field of view. But the point here is the camera's field of view is all the camera can see. Anything outside the field of view, the camera can't see, so it's completely disregarded. So here we have 3 pedestrians that the camera has identified in the crosswalk. So my point being, if there was a 4th or 5th pedestrian off to the right, just about to step off the curb, the camera's not going to see them in this example until they are within the camera's field of view. Every camera also has a 0 point, the center point to its field of view. So when we're looking at something like this scene here, we've got 3 pedestrians directly in front of us. We've got cars parked off to the left in nearby, and in the far distance, there's a couple of vehicles parked off to the right, 2 of them in what appears to be a driveway. There's a car parked way down the road. You'll see that there's a sign there for a school speed zone limit. But I'm willing to bet that as you followed me around and looked at all these different objects, you moved your eyes. You moved your eyes to look around within the camera's field of view. Well, the camera can't move its eyes. So think about this. Stare at the red dot, the camera's center point. Stare at the red dot in the middle of the field of view. And without moving your eyes, can you identify the parked cars, the traffic signs, the number of pedestrians, things like that? It gets to be difficult because we're built to move our eyes. Well, the camera has to take in all the information in its field of view and process that. In order to do it accurately, one, it needs to know what its center point is. And the reason it needs to know the center point is the camera needs to be able to adapt for varying road and vehicle conditions. As the vehicle load changes, the tilt or pitch of the camera will change. So if we have a vehicle, let's say we're driving a 3-row SUV and we're driving it alone and no load in the vehicle and the gas tank is almost on empty, this vehicle is going to be pitched down a bit and the center of the camera is going to be pointing low. However, the camera can still see everything that's within its field of view to process if it's calibrated properly. So as the vehicle load changes, we now have 7 passengers in the vehicle, a full load of cargo or luggage, and the gas tank is full. Now the vehicle's squatting a little bit in the back, and the camera is pitched up. The center of the field of view is looking up, but the camera still needs to be able to detect the the pedestrians directly in front of our vehicle. So it can adapt for those changing vehicle conditions. If we perform a service that changes where the camera is pointing and we don't calibrate, we take away the camera's ability to fully adapt left and right and up and down, to the point that the camera may not be able to recognize a danger, a pedestrian, a vehicle that's approaching quickly, because its center point is now skewed off to one side or another because it's not properly calibrated. So what a camera does in many vehicles is the camera module performs a test. It's called a vanishing point. And when the vehicle is actually driving on a straight, flat road for an extended period of time, what the camera does is, with its center point fixed, it looks at either the lane lines or the edges of the road and follows them to where they disappear on the horizon. And this is just a validation or a check of its calibration status. Not every vehicle manufacturer does this. Mazda is one that does. And if you're driving, let's say we're driving through South Dakota where the roads are nothing but flat and straight, after a long period of time, the camera will be able to tell that it's fairly well calibrated because its center point will fall at the point where the left and right lane lines or road edges merge together. If the center point and the road lines don't match up, depending on how far they're off, some vehicles can actually set a fault code for being out of calibration. But I will tell you, most can't. So this camera center point, what we are doing when we calibrate is we are placing a target at the exact distance, the exact height, and in the case of multiple targets, the exact spacing that the OEM requires. And we are setting up the vehicle in the exact conditions that the OEM calls for. So the camera's center point, if it's calibrated properly, should exactly match the center point of our target. So when we properly precondition the vehicle and we set our target properly and we perform a calibration, we're bringing the camera back and teaching the camera what its true center point is. It's called a 0-point calibration. So that's really what we're doing when we perform just about any camera or radar calibration. We are teaching, it's actually called learning the camera or radar sensor where it should be looking, what its center point is. Now, I just want to add the calibration part is fairly simple and straightforward. Radar sensors, on the other hand, have an extra step. Radar sensors also need to be mechanically aimed before they can be calibrated. So you mechanically aim a radar sensor anytime it's been removed from the vehicle and reinstalled in any way disturbed, or there's several repairs that you may perform that would require the radar to be re-aimed and then recalibrated. So aiming gets the radar sensor to be pointing straight ahead on the vehicle center line, but also perpendicular to the ground. So at a true right angle to the ground, or the exact number of degrees from a right angle that the OEM calls for. Once it's set on that point, then it can be calibrated, and then that particular radar sensor is good to go. So let's take a look at some of the services. This is by no means an exhaustive list, but some of the services that we may perform that would require a camera or radar sensor to be recalibrated. So on the camera side, camera calibration really tends to fall into the realm of glass replacement. So you replace a windshield, whether it's repaired or replaced, anything that would be in the field of view of the camera, any type of a repair would need to be recalibrated. If the camera is removed from its bracket and snapped back in place, it needs to be calibrated. Now, here's the next ones are where a lot of shops weren't aware that these services directly impact the accuracy of ADAS systems and the ADAS system's ability to perform a wheel alignment. So we're going to get into wheel alignment in just a little bit, but a wheel alignment changes where the vehicle is pointing and where it's driving, which will directly change where the camera is looking. So changing a wheel alignment, changing front toe, changing rear toe, anything that you adjust with rear thrust angle would require an alignment. On most vehicles, any change in ride height, you have tires that are slightly larger than OE. You put on new springs, minor suspension modifications. And I say minor, most vehicle manufacturers don't allow for lift kits and lowering kits on vehicles to also be calibrated. So it depends on the OE. Nissan pickups and SUVs, they have an allowance. How much height the vehicle was raised can be input into the scan tool, and it can still be accurately calibrated. Newer Ford pickups and SUVs. We're working on a 2020 Ranger the other day, and playing with the calibration, we found that it allows for up to a 13-inch lift kit to be installed and still be calibrated. But again, each OEM is specific to their software in a particular vehicle. General Motors on a Chevy pickup only allows a 2-inch lift kit. So it's really important that you look into what the OEM will allow. So again, changes in tire size to a point. Some vehicle manufacturers, Honda, Volkswagen, Audi, some Fords, will ask you to measure the ride height at either all four corners or at least the front two sides of the vehicle, the wheel arch opening height, and you input that into the scan tool, and the software and the camera or the radar can adapt to that change in ride height within reason. So the camera or radar knows its exact height from the top of the wheel arch opening to the sensor or camera. What we're telling it is how high the wheel arch opening is off the ground, and then it just puts two and two together to calculate its new camera position. And if DTCs are present in an ADAS system, besides clearing the DTCs, the system will also need to be calibrated. Now, here's some tricky ones that come into play with radar calibration, especially forward-facing radar calibration. If a radar sensor, again, is removed and replaced, we just took it off while we're doing a service and we bolt it back in place, it must be calibrated. Minor collisions, collision repair, a bumper cover that's repainted, fenders and quarter panels repainted may require blind spot radars or forward-facing radars to be calibrated. It depends on the vehicle manufacturer. You know, vehicles like Volvo with radars behind the bumper covers, they don't allow their bumper covers to be repainted because they have a very specific type of paint, and any other type of paint could interfere with the operation of the radar sensor. So body shops have to purchase pre-painted bumpers that match the original vehicle color. If a bumper cover has to be removed for any type of a repair, or if a grill has to be removed and reinstalled. So think about a radiator, an AC condenser, transmission cooler. On some vehicles, an air conditioning compressor may require the front bumper or grill to be removed to service. Well, when we replace or remove the front end of the vehicle, like on my old Chrysler Town and Country, you have to remove the whole front bumper cover and grill. When it's replaced, we've changed the position of the radar sensor, and it would need to be calibrated. And again, wheel alignment changes where the vehicle is pointing, and it'll also affect the forward-facing radar, as well as DTCs being present. So I get a lot of questions about wheel alignment and ADAS calibration. I just did a real quick search in some service information systems. This happens to be in Mitchell, looking at a 2017 Toyota Camry. And we're looking at the calibration procedure for the forward-facing or lane departure warning camera. And it says if toe in is adjusted, not specifying front or rear, if toe in is adjusted, the camera must be calibrated. They call it a camera adjustment. But in the same information system, we look at a 2019 in the same calibration procedure, there is no mention of alignment requiring a camera calibration. However, if we look at the parts and labor guide, the procedure or the labor for performing a camera adjustment or calibration specifically says it does not include wheel alignment. So what's Toyota trying to tell us here? By matching wheel alignment up to the labor time for a camera calibration. The reason I bring this up is if we're looking at the calibration procedures, it won't always say specifically that if an alignment's done, it must be calibrated. Sometimes it might say, if you're going to calibrate, it must be aligned, but you may have to look in different parts of the service information system to find exactly what you're looking for. And unfortunately, it changes by vehicle manufacturer. So for instance, if we were to look up the wheel alignment procedure for this particular vehicle, it may tell us that we may have to perform one or more calibrations. If we looked up this same vehicle in Toyota's or even Mitchell's collision information system, Toyota makes no question about it. If you perform a wheel alignment, Toyota says you must calibrate the forward-facing camera and the forward-facing radar. But they don't say that in the vehicle repair information system. Kind of contradictory. So it makes it difficult for us as shop owners and service technicians to determine exactly what needs to happen when. I know some people say if the OEM doesn't specifically say it, they're not going to do it. And I understand that. But we also need to understand where service information comes from. Well, it's not and has never been intended for the aftermarket to repair vehicles. OEM service information was written specifically for OE dealerships to help mitigate warranty costs. It's not about exactly how the vehicle works or everything that's necessary to fix it. It's what does a dealership technician need to fix the vehicle as quickly and with as little cost as possible when it's under warranty. I have many opportunities to speak to OEM ADAS engineers as part of my job. And just having a chance to sit down at dinner one time with multiple ADAS engineers from several different OEMs, Ford, FCA, Toyota, Honda. There was one other I don't recall. But when I asked them about service information and how come they're not more specific in what they are trying to say in their procedures, all four of them or five of them dropped their head and shook their heads. You could tell that this is an ongoing issue for them. So one of them told me that when the engineers write a service procedure, it is very long and very detailed, very, very specific. But that very specific service process is given to the technical writing team, who then rewrites it so, and I quote, automotive technicians will understand it. They leave out details. And I'm going to give you an example here on this 2019 Subaru Forester. So here we're looking at the calibration procedure for EyeSight, their forward-facing camera. And it tells us that the front wheels need to be directed in the straight ahead position with the steering wheel being set to center. Now, according to the engineers, what they really mean to say is the front wheels need to be directed in a straight ahead position. The steering wheel needs to be centered, and the steering angle sensor needs to be set to 0.0 degrees. It goes on to say in the note, if you can't do that, if you can't get the wheels pointing straight ahead with the wheels centered and the steering angle sensor at 0, the vehicle needs to be aligned. So in this indication, Subaru is saying you may have to align the vehicle before you calibrate. But if we go to the alignment procedure, so we just performed an alignment on the same Subaru, it says when an alignment has been adjusted, we need to clear the lane keep assist learning value from the EyeSight module. In doing so requires that we also perform a calibration. So what I'm getting at is in the alignment procedure for this one vehicle, if you align, you must calibrate. But in the previous, looking at the calibration procedure, it only tells us that we might need to align before we calibrate. They're not always simple and straightforward. Many times it takes a lot of research going through multiple pages of service information to really get down to the details of what's needed when a vehicle is serviced. So I get this question very, very often. If a vehicle is aligned at the end of the assembly line when it's manufactured, and the camera is calibrated at the end of the assembly line, the customer, the consumer, takes the vehicle out and drives it. over a period of time, suspension components wear, and then eventually the vehicle comes into your shop and an alignment is needed, and you repair the suspension and you perform an alignment and you get it back to OEM tolerance. If the camera was calibrated to OEM specs before you worked on it, wouldn't the camera still be calibrated to OEM specs after you aligned it? Well, good question. And the simple logic might seem like that would be the case. However, it depends on time. How long, let's say this customer's vehicle, the customer hit a pothole or a curb and it threw their alignment out. How long did the customer continue to drive the vehicle before they brought it to you for an alignment? Did they hit a curb and come right to your shop? Or did they hit a curb and drive it for 6 months and then eventually now the tires are worn and they brought it in for an alignment? Time is the real key here, and let me show you why. So here we're looking at our vehicle in blue following another vehicle, and the blue line is the vehicle center line where the vehicle is pointing. Critical ADAS features are based on the vehicle center line. When I say critical ADAS feature, the forward-facing camera mounted to the windshield, the forward-facing radar mounted behind the grille or behind the bumper, those are aligned to the vehicle center line. So it's where the vehicle is pointing. The thrust angle in red is where the vehicle is driving. If the vehicle is properly aligned, the thrust angle and the center line are the same. Where the vehicle is pointing is where the vehicle is driving. However, if we have a vehicle that's out of alignment, and of course it's exaggerated here, the vehicle is still driving straight down the road. The thrust angle, we're correcting with the steering wheel to guide the vehicle straight down the road. However, the center line is now not pointing straight down the road. It's pointing, in this case, far off to the left, which is also where the camera and the radar are looking. So that will directly impact the accuracy and the ability of the camera and radar to perform their jobs. So this particular vehicle, and here's where time comes into play. And I mentioned earlier that with the camera's field of view, it has the ability to adapt and learn to varying vehicle conditions. Well, alignment is one of those variables that a camera or a radar can adapt to. So over an extended period of time, in this case, the forward-facing camera in green, which was aligned to the vehicle center line, that line in blue, over an extended period of time, the camera is starting to adapt. It knows that the vehicle center line, where it was looking, is not truly where the vehicle is driving, because it monitors the steering angle sensor for one. And as the driver is continuing to have to correct for the vehicle being out of alignment, the camera or radar will begin to adapt to the driver's adapting to the vehicle being out of alignment, but only to a limited degree. So the camera gets better at what it does over an extended period of time, and it could be weeks, it could be months before it can fully adapt, but it'll eventually hit the limit of its adaptation and it'll stop. Some vehicle manufacturers will cause it to set a code. Others will just allow it to go on and not give any indication that there's an issue. So running a DTC scan for one, and the camera says there's no fault codes, that doesn't mean it's properly calibrated. So this vehicle comes in after 3 months and the tires are worn. The consumer says, I think I need a wheel alignment. Of course they do. You also sell them a set of tires, align the vehicle, do a steering angle sensor reset, and we get the center line and the thrust angle matching. They're now properly aligned, and the thrust angle and the center line are the same, and they're both straight down the center of the road and matching vehicle center line. However, we didn't calibrate the camera. So what we did was now cause the camera to be skewed in the opposite direction. It was pointing here to the right of center line. That's where it adapted. And here it's still pointing to the right of center line. And over an extended period of time, it may be able to adapt back to vehicle center line, but we have no idea how long that might take or if it even can adapt. In the meantime, if we turn this vehicle back to the consumer while they're driving it and waiting maybe a few months for the camera to readapt, we are now in a state of liability limbo. If anything occurs to this vehicle that an attorney can tie back to a service that anyone performed, and then tie the lack of ADAS calibration to the repair we performed, we can have an issue. But at the very least, this could be a dangerous situation for the vehicle owner when they're driving. If the camera can't see what's directly in front of the vehicle, an accident can occur. So when we also perform the forward-facing camera calibration, now the thrust angle, the vehicle center line, and the camera are all aligned. Now there is another variable. If after this alignment and the vehicle had adapted, we recalibrate the camera and bring it online. If this vehicle uses the camera and the radar sensor together, the camera and the radar sensor will now be out of sync. It may set a code, it may not, but again, depending on the vehicle, the system may need more than one calibration after a wheel alignment. So when it comes to calibration, there's really two types of calibration that we're going to be looking at. The first is a dynamic calibration. Dynamic calibration is performed with a scan tool, and it's done while the vehicle's being driven under very specific OE required conditions. Now, every vehicle manufacturer has slightly different conditions, but some common ones are good weather conditions. It's got to be during the day, can't be raining, snowing, can't be foggy. The camera, in this case, needs to be able to see the lane markings, other vehicles on the road, objects on the side of the road. Speaking of lane markings, they must be clearly identifiable by the camera. I know personally, many roads around where I live, the lane markings are not clear. They're worn away. They're inconsistent. That may cause a dynamic calibration to take an extended period of time, or may just cause the calibration to fail. So many vehicle manufacturers, if not most, are also looking for objects on the side of the road. Fire hydrants, guardrails, pedestrians, parked cars, mailboxes, garbage cans, billboards, things like that. It counts the objects, and when it gets to a certain point and it can identify enough objects, the calibration will be complete. Most vehicle manufacturers during a dynamic calibration, since you have the scan tool with you, and if there's someone else in the vehicle who can monitor the scan tool, you'll see a progress bar, generally in percentage. That progress bar is indicating that we have counted up enough objects for the vehicle to calibrate. So every dynamic calibration is going to require a certain minimum vehicle speed. 32 miles an hour is a common minimum. There's some that are a little bit lower, some that are higher, but there's also a maximum vehicle speed. So the vehicle manufacturer or the scan tool software will indicate to calibrate this forward-facing camera on this General Motors vehicle, you have to drive between 32 miles an hour and 67 miles an hour. Minimal lane changes, flat road, minimal curves, minimal traffic. Well, what if you're driving and you come to a stop at a traffic light? Most vehicle manufacturers will just pause the dynamic calibration. When you start driving again and you get back to the required minimum speed, you'll see the progress bar continue and start to accumulate points as it identifies objects until the calibration is completed. When the calibration is completed, you need to follow the instructions on the scan tool Road test the vehicle, make sure everything works. Most vehicle manufacturers will want you to cycle the ignition after the dynamic calibration before you road test, keeping in mind cycling the ignition is more than just turning the key off and on again. Once the key is off, the driver's door needs to be opened. I'm sure you all have experienced, you turn the key off in a vehicle, the radio continues to play until the door's open. It's really the door opening in conjunction with turning off the key that shuts down the vehicle. So that needs to occur in many cases for a specific amount of time, 10, 15 seconds, before you restart the vehicle, take it for a road test, bring it back to the shop and perform a post scan after your calibration. The other form of calibration is a static calibration. Static calibration OE requirements include a controlled environment. So they want calibrations done indoors, bright, even controlled lighting, no shadows on the target, no glare or light hotspots on the target, no windows. Many vehicle manufacturers will specifically say the calibration must be performed in a windowless environment. You'll also see some manufacturers say calibration must be performed in a windless environment. That's because the OE calibration systems are fairly lightweight, and in certain circumstances, the targets are large. And if you have a crosswind through your shop, that large target turns into a sail and it could throw your calibration system across the shop. No need to worry with the Autel system. It weighs 185 pounds. It's not going anywhere. No background clutter. No, let's get back to no windows. That doesn't mean you have to seal up your windows. It just means that you may have to temporarily cover them with a shade or with a piece of cardboard. Toyota specifically does not allow windows behind the target, windows that the camera can see. It will cause glare in the eyes of the camera and it'll fail part or all of the calibration. No background clutter. The camera is specifically looking for a very specific target in a very specific place. And if there is clutter in the background that could look like the pattern, the target, it could miscalibrate. I've seen many instances where there's so much clutter in the background, especially toolboxes and things like that, that could be in a black and white checkerboard pattern, that it can cause issues and either fail a calibration or cause a miscalibration, an inaccurate calibration, in which case there won't be a fault code for that. It's just the system won't act properly. I had one example of a tire shop in Ohio that was getting into ADAS calibrations. They bought one of our systems, and the very first vehicles that they attempted all failed. They couldn't get the calibration to complete. So they wanted to return the system. I went out to do some training. And as I walk into their shop, big, gorgeous, wide open shop, they got a fantastic area for doing calibrations, a large flat level area. But in the background was their tire rack, floor to ceiling tires. The wall behind it was white, but the rack wasn't completely full. There were missing tires. So from a distance, it was a black and white checkerboard pattern. So every vehicle they tried to calibrate is a black and white, either checkerboard or circular pattern, and the camera was confused. So when we told this to the shop owner, he got very upset. He thought they were going to have to take down the tire rack and move it and maybe build an outbuilding to store tires. It doesn't have to be fancy. You look at Toyota's OE solution for blocking out background clutter. They have another technician with a 3 foot by 3 foot piece of cardboard stand behind the target. It could be a shade or a large piece of cardboard. It could be something like Hyundai, Kia, or Subaru recommend, a roll around whiteboard that you put behind the targets so the camera can't see the background clutter. As long as the camera's field of view is free and clear of clutter and all it can see is the target, you shouldn't have a problem. Flat level floor. Now, this is an OE requirement, and it's an important requirement because the flat level floor helps us determine the exact pitch or angle of a camera or radar sensor prior to calibration. If the vehicle's not sitting flat and level, the calibration cannot be accurate. That's why a lot of shops are performing ADAS calibrations on their alignment lift. Then, of course, you need all the different targets and patterns and accessories for the different vehicle manufacturers and systems that you want to calibrate, as well as the calibration procedures and the measurement specifications. You can see here we're doing a Volkswagen forward-facing camera calibration, and the OE will tell us exactly how far from the front bumper that target needs to be placed, exactly how high the center of that target needs to be, and how square and how centered that target needs to be to the vehicle. So in the procedures and the specification guides from your service information system, you would get that type of information. That information is also built into the Autel ADAS calibration software to make it easy. So that was static and dynamic calibrations. There are some vehicles that do both. Hondas, for one. On certain Hondas, they have a calibration that is, it's called a dual calibration. You calibrate statically, and then you immediately take the vehicle out and do a dynamic calibration that must complete within 30 minutes, or you have to redo the static. Actually, if you calibrate statically accurately, the dynamic calibration generally takes 5 to 7 minutes. It's not that big a deal. Hyundai Kia. Now, some Hyundai Kias were very clearly state in the calibration procedures that after you perform the static, you must perform a dynamic. However, many times Hyundai Kia Service Information System says after you perform a static calibration, you need to perform a test drive, or sometimes called an action test. And the test drive has parameters. You need to drive between 32 and 67 miles an hour, good weather conditions, clear lane markings. Well, that sounds an awful lot like a dynamic calibration. It is. They just don't use that same terminology. They call it an SPC, single point calibration. So on those Hyundai Kias, where it says to perform a test drive under certain driving conditions, that is in fact a dual calibration. You're performing two separate calibrations, and you should charge for two separate calibrations. Mercedes-Benz. On Mercedes vehicles with a stereo camera, you again perform a static calibration and then take it out for an intensive dynamic calibration, which could easily take 45 minutes. It's a very unique static calibration. They do things quite differently than other vehicle manufacturers. But again, it is a dual calibration. But one thing that they do different is the static calibration is for the right-hand camera lens, and the dynamic is for the left lens. Kind of strange, but different. Subaru is one of those vehicle manufacturers that does not use the terminology static calibration. They again call it a test drive or an action test, or they'll ask for the vehicle to be driven to complete the calibration. Now, many technicians think that means just disconnect the scan tool after the static, take it out and drive it. And if it works, you've completed the dynamic portion of that calibration. Well, that's not the case. If you read Subaru's service information, they very specifically state that after the static, the vehicle needs to be driven with the scan tool still connected until the calibration completion PID displays a specific value. It's a 0F, a 1F, or a 3F. Your service information will tell you what to look for. But the vehicle needs to be driven with the scan tool attached. That is a dynamic calibration. Otherwise, the calibration is never truly completed. So many calibration techs are calibrating Subarus, returning the vehicle to the consumer, and never finishing the calibration. Even taking it for a road test, if you've disconnected the scan tool, that vehicle won't complete its calibration. So where's the industry headed? Where are we, and where's it going? So if we look at model year vehicles 2009 through 2021, currently 58% of vehicles on the road in the United States are statically calibrated, static only. This number has increased over the past year. There's 35% of vehicles that are dynamic only. This number's dropped a few percentage points over the past year. Static and dynamic, in other words, dual calibration, actually it's 8%. I forgot to edit the actual note here. Static and dynamic calibrations are now at 8%. And there are some vehicles, like certain Mazdas, that are an either or. You can perform a static or a dynamic, and those account for approximately 2% of the total car park in the United States. So if you add this up, if you think about what kind of calibrations are you going to perform in your shop, how many real vehicles are going to have some form of static versus some form of dynamic. If we look at this in total, if we look at 58% that are static only, 8% that are static and dynamic, and 2% that are static or dynamic, that means 68% of the vehicles have some form of static calibration. This number is going to continue year after year. Dynamic, if again, you add up dynamic only at 35%, static and dynamic at 8%, and static or dynamic at 2%, 45% of the vehicles on the road have some form of dynamic calibration, and this number is dropping year after year. The reason these numbers are changing is, of the vehicle manufacturers that are right now doing just static, you look at Toyotas, most Hondas, all Subarus, all Hyundai Kias are at least mostly static. Most of the major European OEMs, except for Volvo and BMW, they're all, for the most part, static only. When we look at the vehicles that are dynamic only, BMW, Volvo, and in the United States, General Motors, Ford, and Chrysler products, those vehicle manufacturers are finding that dynamic calibrations are becoming increasingly more difficult to complete, mostly because of traffic conditions. If you recall, when we were on the dynamic calibration slide, most OEMs call for minimal traffic because you need a space, a free and clear space in front of the vehicle being calibrated in order for the camera to be able to detect objects. But it's not just traffic. It's also weather conditions. If it's raining, snowing, foggy, the camera can't be calibrated. If there's snow on the ground, leaves on the ground, if the camera can't see lane markings clearly, the dynamic calibration can't be completed. So what domestic OEMs have found is they end up, because of liability concerns, either holding on to the vehicle and not being able to return it until they can perform a dynamic calibration, or returning the vehicle to the consumer uncalibrated and praying that they don't have a liability issue if something should happen to go wrong. So this is something that what I'm going to tell you next that really surprised me. But there was a meeting a year and a half ago that included General Motors, Ford, and Chrysler to discuss the topic of moving to static calibrations for those OEMs. And I didn't know that there was this much cooperation between the Detroit Big Three, but they worked on this ADAS task force, and they determined that they are all going to move forward with static calibration at some point. And the group decided that Fiat Chrysler, the Chrysler Dodge Jeep vehicles, would be the first to switch over to static only calibrations, beginning with the launch of the 2021 Jeep, the extended length Jeep WL, the Jeep Grand Cherokee WL. So that vehicle is going to have static calibration for forward-facing camera, for forward radar, and for forward night vision. General Motors and Ford, working with FCA, are going to monitor how well the static calibration is being received by the dealership owners and the dealership technicians, and then they are going to move forward with adding some form of static calibrations to their dealerships as well. Now, I can let the cat out of the bag because the deal is done. The order has been inked and the product has already been produced, but Autel is the supplier of OEM calibration equipment for FCA North America. And we are also going to be the calibration equipment supplier for not only FCA Europe and Asia, but as well as Fiat, Alfa, and Peugeot eventually. And General Motors and Ford are watching very, very closely on how well our calibration system performs at the FCA dealerships before they jump on the bandwagon and start looking at a ADAS calibration system for their own dealerships. Not saying that they're going to choose Autel, but they're looking at what FCA did. FCA tested our product for 18 months. We developed a custom night vision calibrator. They're using the Hyundai Kia target for forward-facing camera calibration, and we developed a very custom tilting radar plate for their forward-facing radar calibration. So you'll be hearing a lot more about that with the launch of this new Jeep Grand Cherokee WL in mid-March or early April. Well, that's it for today's session. If you have any questions, go ahead and unmute yourself and ask away, or if you prefer, go ahead and enter your questions into chat, and I'll stick here for as long as anyone wants to talk. I hope everyone can join us in 2 weeks. We're going to start getting into the much more technical information with ADAS best practices on February 10th. That's going to be a little bit longer class. It'll be between 90 minutes and 2 hours, just to give you a heads up. But again, it will be recorded, so you could watch it at your leisure. But that's really going to be the class that's going to tie all the previous 4 sessions together before we actually get into myths and misconceptions, and then finally live demonstrations of ADAS calibrations. So, any questions?
I don't see any in the chat. I do see a thank you from Danny. Thank you for that note, Danny.
Appreciate that, Danny. I appreciate you joining us.
Thank you all very much.
Thank you too. Ryan, John, you kind of have a quizzical look in your eye. I know you're not sharing your camera. I'm just kidding. No,
I'm here. I just want to say thank you as well. Very informative.
Oh, thank you. I appreciate that. I'm sorry. I was just messing with you there. But if any questions do come up, you can always send them to Maddie and she'll get them off to me. And I can answer questions through text messages or email.
All right.
That's it. Thanks, everyone.
Thank you.
Thank you.
And